Hi and welcome to this clip on organometallic compounds to do with alkyl lithium and grignard reagents. It's an extension clip designed for A-level students and it links into many first-year universities degree studies on organic chemistry where organometallic compounds are introduced. So this clip is designed to help you sort of bridge the gap between A-level and university level. So before we start going into the actual alkyl lithium and grignard reagents themselves, we need to just touch upon an idea that maybe isn't covered in some A-level syllabuses called Lewis acid-base theory. So you've probably done Bronsted-Lowry acid-base theory, which is the idea of protons being accepted or donated. Now at the same time, what will happen is an electron pair will be accepted or donated. So looking at the acid and base behaviour in terms of electron pair transfer, that's where we come up with the definition of a Lewis base or Lewis acid. So you can obviously apply the same idea across to acids as well as bases. So if we take the simplest example of this, which is the interaction between a proton and a hydroxide ion to make water. So we can represent this as a little curly arrow mechanism. The electron pair, the lone pair on the oxygen, can be donated to the proton. So the OH accepts a proton but donates an electron pair, and the proton accepts an electron pair but donates itself. So obviously any substance able to donate a proton would behave in a similar way in the presence of an OH- ion. Okay, now we've established what a Lewis base is, we can actually start talking about the reagents in hand. So alkyl lithium compounds are based around the polar covalent bond that can form between lithium and carbon. Now technically, from GCSE and probably through most of A-level, you're used to the idea that non-metals gain electrons and metals lose them. But if we have a think about where lithium and where carbon are placed, there's an electronegativity difference, but it's not sufficient for carbon to be able to take the electron out of lithium's outer shell completely, in the same way that a halogen might. So we get what's called a polar covalent bond, and that has a dipole that I've illustrated. So a quick look at the periodic table allows us to illustrate this. So as you can see, there's sufficient electronegativity difference between lithium and carbon for a polar bond, but not enough for an ionic one. So if we put this into an organic context, you can see that lithium can be bonded to alkyl groups. So if we put the dipoles in, you can see quite easily how you could get an electron pair moving onto that carbon. That would then give the carbon a negative charge, which means you get a negatively charged methyl carbanion. So this is different from a carbocation that you might have heard of. Carbocations are positively charged. A carbanion is negatively charged. So it says it's an electron source, which is true. It's also a nucleophile. It can also be considered a Lewis base, like we talked about a little bit earlier. So you can also think of this in terms of Bronsted-Lowry acid-base chemistry. And this might help give it a bit of a bridge or a bit of context for you if you're looking at this clip as an A-level student. So you'd obviously get conjugate bases and all that kind of thing setting themselves up as well. Notice that the Ka value is very small because alkanes are obviously very, very weak acids. So some common examples of organometallic compounds is not just lithium-based compounds we're talking about here. We can also talk about magnesium-based compounds, so-called grignard reagents, that we'll talk about a bit later, and also copper-based organometallic compounds. There's other metals as well that will do this. So they're all excellent nucleophiles for the same reason that they'd be Lewis bases, like we talked about before. And we make them by reacting an alkyl halide with your active metal of some kind. It could be lithium, magnesium or zinc, for example, and that gives you your organometallic compound. It has to be done in dry conditions because these compounds themselves react with water, so we use an ether solvent. An example might be ethoxyethane. So, just to have a quick look at what we've covered so far. Before we start looking at Grignard reagents, let's just summarise. So organometallics, in general terms, are compounds with a carbon-metal bond. There's a difference in electronegativity between the carbon and the metal itself, but not enough to form an ionic bond, so you get a polar covalent bond instead. And some common examples would be organolithium, which we've just talked about. We can sometimes refer to them as alkyl lithium if it's just an alkyl group, but there's nothing to stop an aromatic group also being bonded to a lithium. So we can have organomagnesium or organocuprate. We can also have organozinc, organomercury. Lots of different metals do this, like we mentioned a second ago. So let's now go on to look at Grignard reagents. So Grignard reagents are the ones specifically where magnesium is bonded to an alkyl group. So they were first developed by a French chemist called Victor Grignard, and it's quite straightforward to make them. All you have to do is take magnesium and react it with an alkyl halide of some kind in an ether solvent like we talked about a moment ago. And that gives us our Grignard reagent on the right hand side there. So here's some examples of Grignard reagents. You can see that you can have any halogen or any carbon-based organic section of the Grignard reagent molecule. So let's now look at the summary of Grignard reagents. So some of these compounds you might not have heard of. You'll have heard of aldehydes and ketones, maybe if you're an A-level student, but you might not have heard of epoxides. You will definitely have heard of esters before. So I want to try and explain a little bit about what they mean by an H+ workup as well. So first let's remind ourselves what Grignard reagents do. They, very much like alkyl lithium compounds, generate a carbanion which acts as a Lewis base. So this has the effect of adding a carbon-based group to an organic compound, creating a new carbon-carbon bond. So in this process, the Grignard reagent will actually form an intermediate compound on the way to making the product, and this compound needs to undergo acid hydrolysis before you can get the product. So that's why I've got in all of these reaction schemes here an H+ workup. So let's just illustrate that a little bit more. So if we take an example of a Grignard reagent reacting with a ketone. Initially you've got an organometallic compound, but it's got magnesium in it from the Grignard reagent. We don't want this attached anymore. So we add an acid in the form of a hydronium ion, which protonates the molecule at the oxygen atom and releases MgOH-Br. So let's just think about what's happening and where. If we go back to the very beginning, top left-hand corner, we've got our Grignard reagent, and we're reacting it with a ketone. Now the reason we're doing that is because we want to make a new carbon-carbon bond. But the problem is we don't need the MgBr once that new carbon-carbon bond has been made. So in order to get rid of it, we need to add the acid afterwards, which will actually hydrolyze that compound and then produce our final product, and the MgOH-Br will come off separately. So you can see hopefully with my annotations what's been protonated and what's been removed. So now we're going to look at an exam question. It's actually from an OCR paper, and it would have been very challenging for the candidates who took this particular paper. But if you take a few minutes to just have a look at the top part of the question, you can see quite clearly that they've summarized some of the things we've talked about during this clip. So they want us to complete a mechanism for stage 1, where you've obviously got an alkyl lithium compound, which is denoted here by RLI, reacting with benzaldehyde. So the first thing to remember is that the carbon double bond oxygen will be polar, and the R- will be our Lewis base, or our carbanion that we talked about a few minutes ago. So we put the dipoles in on the C double bond O, and then we can just remind ourselves what the role of the R- is, and then we can put a curly arrow onto the R- and point it at the carbon that has the delta plus on it. So the next thing to do is to think about what happens at the carbon double bond oxygen. So the pi bond will break, and that allows us now to put an intermediate in. So remembering that they only actually ask us for the mechanism for stage 1. But seeing as we're talking about the mechanism, I'm going to go a little bit further and add a part to the intermediate to show what happens. So you can see in stage 2 you've got an H+. So I've put in blue a little bit of extra on top of what they wanted in the intermediate box, so you can see where the H in the final product actually comes from. Okay, so let's move the page down a little bit to try and do the final part of the question. Okay, so it says that the chemist needs to prepare the organic compound below from benzaldehyde. And it says draw the structure of the alkyl lithium compound needed for this synthesis. So to do this we need to think carefully about which part of the molecule came from where. So the C6H5COH and then the H on that, the part in red, came from the benzaldehyde originally. And obviously in the mechanism we've just drawn it's a nucleophilic addition. So the nucleophile must have been the rest of it. So taking this into account, we can now draw the structure of the original alkyl lithium compound. Okay, so that takes us to the end of this short introduction to organometallic compounds. Hopefully it's been quite useful, and as always, thank you very much for listening, and until next time, see you soon.